Vernier calipers is an instrument which is most commonly used in the physics laboratory to measure lengths of small objects accurately, which could not have been possible with a meter scale. The word calipers means any instrument with two jaws which is used to determine diameters of objects. Vernier calipers was invented by a French mathematician, Pierre Vernier, in 1631, and thus the name Vernier calipers. It consists of a long rectangular metal strip which has a fixed jaw on one end. It is graduated in inches at its upper end and centimeter at its lower end, which is called the main scale. There is a movable rectangular metal strip which is graduated with a special relation to that of the main scale, which is called the Vernier scale, which slides over this long metal strip. It has a jaw similar to that of main scale. These jaws together are used to hold the object firmly while measuring its length, which is not possible with a meter scale. These jaws are called the external or lower jaws, which are generally used to measure the diameter of a sphere or a cylinder. These jaws are extended to other side, called the upper or the internal jaws, which are generally used to measure the internal diameter of a hollow cylinder. There is also a metal strip attached at the back of the Vernier calipers, which is used to measure the internal depth of a cylinder. This instrument works on a simple principle known as the Vernier Principle. According to the principle, a given length x is divided into n-1 and n smaller divisions, each division of different lengths, which are represented by two scales as shown. Let us say the distance of 9 mm is divided into 9 divisions on one side and 10 divisions on the other side. Then 10 divisions of scale B is equal to 9 divisions of scale A. 10 into B is equal to 9 into A. B is equal to 9A by 10. B is equal to 0.9 divisions on scale A. Here, the upper scale, scale A, is called the main scale, and the lower scale, scale B, is the Vernier scale. One Vernier scale division is equal to 0.9 main scale divisions. As the length of the main scale division is equal to 1 mm, then one Vernier scale division is equal to 0.9 mm. Therefore, each Vernier scale division is shorter than the main scale division by 1/10 of one main scale division, or 0.1 mm. Thus, as we can clearly see, the first mark of the Vernier scale is short by 1/10 of the main scale division. Thus, 10th mark of the Vernier scale is short by 10 by 10th of main scale division, and therefore 10th division of Vernier scale coincides with 9th division of the main scale. Now, let us try to move the Vernier scale very slowly from left to right. Now, the 0 of the Vernier scale is moved to the right marginally, and the first mark of the Vernier scale still does not coincide with the first mark of the main scale. In this case, we cannot measure the displacement. Now, we try to move the 0 until the first mark of the Vernier scale coincide with the first mark of the main scale. Now, we can firmly say that the displacement of 0 Vernier scale from 0 main scale is 0.1 mm, because first mark is 0.1 mm shorter of one main scale division as explained before. Now, we move even more further such that the second mark of the vernier scale coincides with the second mark of the main scale division. The distance between two zeros is 0.2 mm because the second vernier scale division is 0.2 mm shorter than the second main scale division. Similarly, when the 10th mark of the vernier scale division coincides with the 10th of the main scale division, the distance between them is 1 mm. Therefore, the distances are of order 0.1, 0.2, 0.3, 1 mm or 0.1, 2, 0.1, 3, 0.1, 10, 0.1 mm. Thus, we can say that the least distance that can be measured accurately by the vernier calipers, also known as the least count or the vernier constant, is 0.1 mm. The distance is nothing but the difference between one main scale division and one vernier scale division when both zeros are coinciding. Thus, least count is equal to 1 main scale division minus 1 vernier scale division. In a vernier calipers, where n divisions of the vernier scale is equal to the n-1 divisions of the main scale divisions at any given length. One vernier scale division is equal to n-1 by n main scale divisions. Substituting the value of one vernier scale division in the equation, least count is equal to main scale division minus n-1 by n main scale divisions. Simplifying the equation, we get least count is equal to 1 by n main scale divisions, which is length of one main scale division by number of divisions of vernier scale. After obtaining the least count of the vernier, let us proceed to calculate the length of any given object. Now, let us say a very small object of length x is placed between the jaws. In order to find the length of the object, we need to calculate the distance between the two zeros. In order to find the length of the object, we need to calculate the distance between the two zeros. This can be obtained by subtracting the length from 0 to coincidence of main scale division and vernier scale division, and length from 0 of vernier scale to coincidence of vernier scale. Here, it is 7 main scale divisions minus 4 vernier scale divisions. This can be written as 3 main scale divisions plus 4 main scale divisions minus 4 vernier scale divisions, which is 3 main scale divisions plus 4 into main scale divisions minus vernier scale divisions. 3 main scale divisions is equal to reading that can be measured by the main scale. Therefore, it is main scale reading. It is 3 mm as one division of main scale is 1 mm. Now, this portion is the extra portion between the 3 main scale division and the 0 of vernier scale, which would be measured by the vernier scale and is nothing but 4 into main scale division minus vernier scale division. 4 is the vernier coincidence. Main scale division minus vernier scale division is the least count or the vernier constant as calculated before. It is 0.1 mm. 4 into 0.1 is equal to 0.4 mm. Thus, the length is 3 plus 0.4, which is 3.4 mm. Thus, the formula for total reading is given by main scale reading plus vernier scale coincidence into least count. Thus, we use this formula to find out the total reading measured by the vernier calipers. In some instruments we usually find in laboratory suffer from excessive wear and tear and also due to the manufacturing defect. The 0 of the vernier scale do not coincide with the 0 of the main scale. It is either right or left of it. So, let us say in the given instrument, say vernier calipers A, if the 0 of the vernier scale is to the right of the 0 of the main scale. In this case, a particular division of the vernier scale coincides with the division of the main scale. Now, this can be understood as the vernier calipers is already measuring a certain length as if an object is placed in between its jaws, even though no object is being held. Now, the extra distance is the extra reading. The given vernier calipers is measuring an extra length than the actual length when an actual object is to be measured. Thus, our interest is to measure this extra length. Now, in this device, for example, an interesting point is observed that the fifth division of the vernier scale is coinciding with the division on the main scale when it normally should be at 0.5 mm to the left or right of any division. Thus, we can say that this extra length, which is wrongly measured by this vernier calipers, is 0.5 mm. Therefore, we reduce this length of 0.5 mm from the observed readings to obtain the actual reading. This type of error, in which the 0 is to the right of the 0 of the main scale, is called as the positive 0 error. The correction we make is called the 0 correction, and in this case it is negative 0 correction. This reading can also be simply obtained by using the formula we discussed before. Total reading is equal to main scale reading plus least count into vernier coincidence. Here, main scale reading is equal to 0. Least count is equal to 0.1 mm. And vernier coincidence is equal to 5. Therefore, 0 error is equal to 0 plus 0.1 into 5, which is 0.5 mm. And thus, 0 correction is minus 0.5 mm. Similarly, when the 0 of the vernier scale is to the left of the 0 of the main scale, it actually measures less length than the actual length. Now, let us say, for example, in this given vernier calipers B, the 0 of the vernier scale is to the left of the 0 of the main scale, and the sixth division of the vernier scale coincides with the division of the main scale. But in the normal devices, which are free from the 0 error, the sixth division is actually at 0.4 mm ahead of the main scale division. Thus, we can conclude that this particular device measures a less distance of 0.4 mm. Thus, in order to obtain the actual reading, we need to add this to the observed reading. This type of 0 error is called the negative 0 error, and the correction is positive. As usual, this error can also be calculated using the formula main scale reading is minus 1 millimeters. Vernier coincidence is equal to 6 and least count is equal to 0.1 mm. Therefore, error is equal to minus 0.4 mm and the correction is plus 0.4 mm.